Hello, everyone. Okay. Thank you for joining today's workshop. And I'm Ruki from Privasea. And today we are going to explore a cutting-edge topic at the intersection of cryptography and artificial intelligence, fully homomorphic encryption, and its application in face fear recognition. So this presentation will not only cover the technical aspect of FHE, but also demonstrate how it can revolutionize privacy-preserving machine learning and biometric authentications. Okay, so to give you a roadmap of our journey today, we will go through the following topics. First, the fundamental of fully homomorphic encryption and the essence of privacy-preserving machine learning. The innovation fusion of FHE-based machine learning with our Privasea network. Okay, so and there will also be an overview in Privasea facial recognition application. Okay, first of all, what is encryption? I think encryption involves confusion. So this ensures that the data cannot be understood by any adversary without the key. So it involves transforming readable data known as plaintext into an unreadable format called ciphertext. Only those who have the secret key can convert the ciphertext back to the plaintext and access the rough information. So for example, we can use AES standard encryption to encrypt the Privasea to such a ciphertext. It's not readable, right? So, but this is more for, I think this is more for security considerations. It converts information or data into an unreadable code to prevent unauthorized access. However, it also destroys the readable, or we say the usability or availability of data. But at present, the GDPR in Europe and the DPRAV program launched by DARPA in the United States not only tell us to protect the security during data sharing, but also highlight that the protection of data privacy during its use. So this transition from security to privacy cannot be guaranteed by the traditional encryption schemes, right? So fully homomorphic encryption can solve this problem. It can make data available but invisible. FHE is a special kind of encryption algorithms that allows computations to be performed on encrypted data without needing to decrypt it first. For example, an encrypted x plus an encrypted y equals to encrypted x plus y. This means the sensitive data can still be processed while maintaining its confidentiality. So here is a typical FHE clean and server model that can be used for delegate computation. For example, the client maybe have some sensitive data, maybe medical data, financial data, or even government data. The client encrypts it using fully homomorphic encryption and uploads it to the server, which processes the data in a ciphertext state and returns a ciphertext result. The client decrypts locally to obtain the desired plaintext result. So throughout the entire processing, the whole data is encrypted, even in the transfer row or the cloud. So it can ensure that users' data privacy do not leakage, right? The evolution of homomorphic encryption has been remarkable. It's starting from a partially homomorphic encryption, which only supports one kind of, for example, it only supports addition or only supports a multiplication, and then to somewhat homomorphic encryption, which allowed ciphertext addition and multiplication, but can only support constant numbers of them. And finally, fully homomorphic encryption. It can perform unlimited numbers of arbitrary operations on encrypted data. So among them, now the current mainstream FHE schemes can be divided into two types, maybe word-wise FHE and bitwise FHE. Word-wise FHE includes BGV, BFV, and CKKS, and bitwise scheme including FHE and TFHE. The three inventors of BGV scheme won the highest award in the theoretical computer science in 2022, the Godel Prize. So indicating the importance that the academic and the industry attack to FHE. So next, we will dive into some technical details which will help us understand the currently mainstream FHE solutions and their respective suitable computation types. I think it is crucial for designing applications. Okay. However, if cryptography will make you sleepy, you can give your brain a brief rest, and I will pull you back at the appropriate time, okay? So we started with learning with arrow problem. Now, all mainstream algorithms are designed based on LWE or RLWE problem. It is a fundamental hardness assumption for many cryptographic systems, including FHE and many post-quantum cryptography systems. Okay, it involves distinguish between a set of linear equations with some small arrows and a set of random equations. So in mathematical terms, given a dimension n and modulus q and an arrow distribution over the integer, the LWE problem requires distinguishing between the distribution as plus e, and a uniform random distribution. So A is a random metric, S is a secret vector, and E is an arrow vector. That is LWE problem. The ring learning with arrow problem is an extension of the LWE problem to polynomial rings. So it involves distinguishing between a set of ring equations with some small arrows E and a set of random ring elements. You can see that LWE and RLWE ciphertext naturally has additive homomorphisms. For example, the AS plus E is linear. So AS plus M1 plus E plus AS plus M2 plus E is equal to AS plus M1 plus M2 plus E, right? So the core problem of FHE is how to construct the homomorphism of multiplication. Okay, so how to construct the multiplication homomorphism? The word-wise schemes uses the traditional, maybe a scalar multiplicative. You can see the picture that because the ciphertexts are all vectors, so which cannot maintain their original form after multiplication. You can see that C10, C11, scalar product with C20 and C21. Then we have a 4-dimension ciphertext with the secret key S1 scalar product with S2. That is word-wise schemes. So they propose the key switching techniques and module switching to change back the original ciphertext size. You can see after key switching, the 4-dimension ciphertext are transferred back to 2-dimension ciphertext. It is their original types. Okay, and they use a modular switch to make the ciphertext less noise after modular switching. So it allows homomorphic operations to continue. This is the word-wise scheme. The bitwise scheme is very different. I think it's very interesting because they do not use the traditional multiplication. They use the so-called external product. You can see if we want to calculate M1 multiply it to M2, then you can see this formula. They use M2S and M2. So they construct a new ciphertext tab called RGSW. It construct with RLWE M2S and RLWE M2. It's a new type of ciphertext, and so that's why it's called external product, because it uses RLWE to RLWE and RGSW multiplications, right? So which can see the RGSW ciphertext can be seen as an auxiliary input because it's not the typical tab. So therefore, this type of scheme is very suitable for homomorphic computation in gates and circuits, because you can imagine that if you want to calculate a one-in, one-out gate, it often requires an auxiliary input. So you can use then you can use RGSW ciphertext. Okay. So but we omit to introduce the details here. Then these constructions leave us somewhat homomorphic encryption schemes because they can both evaluate homomorphic multiplication and homomorphic addition, but are limiting numbers because the error it grows. So how to construct fully homomorphic encryption and to realize arbitrary operations? First, we use bootstrapping to solve part of the problem. It can refresh noise. It is the key procedure, but also the performance bottleneck of FHE. The bootstrapping time of word-wise scheme often reaches tens of seconds or even a few minutes. The bitwise scheme bootstrapping faster, but large-scale addition and multiplications are slower. And bootstrapping can be seen as a homomorphic decryption. You can see if you have a full noise ciphertext M, then you can evaluate its decryption circuit AS modulus Q and modulus T. So then you can get a new M ciphertext. However, if the noise growth in the homomorphic decryption is less than the original noise, then you can do more homomorphic operations. Yeah. So that is bootstrapping, is to refresh noise. And how to do arbitrary operations. So for like bitwise bootstrapping, you use functional bootstrapping or gate bootstrapping or even circuit bootstrapping in the LHE mode to evaluate the nonlinear functions. And if you are concentrate on word-wise schemes, then it supports the original multiplication and addition. But for the nonlinear function, you need to approximation using polynomials. Yeah. So in summary, BGV and BFV schemes are good at arithmetic circuit computation over finite fields, and CKKS schemes supports approximate arithmetic circuit computations over real numbers or complex numbers. These two types are referred to word-wise schemes. Okay, and FHE and TFHE is good at Boolean circuit computations, so it referred to bitwise encryption. Okay, then we can try to use these fully homomorphic encryption schemes to construct privacy-preserving machine learning. Why privacy matters? In our digital area, data is often linked to the new oil. So a resource of immense value propelling industries forward, from automotive to finance. However, with great value comes great responsibility, particularly to protect individual privacy. Privacy-preserving machine learning aims to extract value from data while ensuring that sensitive information remains confidential. And machine learning can be divided into lots of types, such as key nearest neighbor, linear regression, logistic regression, neural networks, and so on. And PPML marries these methods with privacy-enhancing technologies. There are some cryptographic techniques such as secure multi-party computation, including double circuit, obvious transformation, and secret sharing. And it allows multiple parties to jointly compute a function over their input while keeping those input private. And differential privacy, it adds noise to data to prevent the output privacy. But today, we will focus on homomorphic encryption, so which is the key technique in Privasea. FHE-based machine learning leverage FHE to enable AI processing. We can see such an example. This is a FHE ML system. At the heart of this system is the protection of sensitive data, which represented here by an X-ray, a type of sensitive, healthy information that requires protection, right? So the client means individuals or entities with private data, such as medical records, that hold the key to potential life-saving insights. And then the server represents the secure and private prediction platform, which in the case is focused on medical prediction without exposing. It uses privacy-preserving machine learning to train or predict without ever accessing the rough data, ensuring that the personal information remains encrypted during in the transfer process and in the server. So it can remain encrypted and secure throughout the process. This is a famous DINN, or we say DIN, demo for handwritten digit recognition. So we use FHE to encrypt the whole image and upload it to the server. Then the server can recognize accurate numbers from the ciphertext image and return the ciphertext result. But the ciphertext result, it contains 10 scores, which if it is 7, then the 7 scores is the highest in among the 10 scores, right? So then the users can find the final result. And you can obtain this demo also from our official website. So FHE-ML offers several benefits. The first one is it ensures data value circulation for AI while maintaining data ownership. And it also provides anonymity and privacy compliance. However, the computation load of FHE is significantly. So it can cause computation pressure on cloud servers. So what if we leverage the power of blockchain distributed computing power? This is our Privasea AI network. It is a distributed privacy-enhancing computation network that allows users to control their data without risk of leakage during AI processing. Especially, we have utilized machine learning techniques to mine the value of data, and then we use privacy-enhancing technologies, especially FHE, to protect users and data privacy, and then distribute computing power on blockchain to provide computing power support the network. And FHE naturally supports PRE, or we say key switching. So the operation result can be distributed by the KMS accordingly. We can use this to solve the key management. So nevertheless, FHE-ML still has a lot of challenges. The main challenge of FHE-ML comes from the complex operation in neural networks. For example, it contains linear operations such as convolution layer, fully connected layer, and nonlinear operations, such as active functions, you say a ReLU or sigmoid. Yeah. So The ML models are always large, and the fictions are complex and FHE unfriendly. We have these two main challenges. And there are some typical FHE-based solutions to solve these two problems. The first, we say, especially CryptoNet, Lola, and Paxos. CryptoNet uses CKKS, so it supports the linear functions like full connect layer, like convolution layer. But when you deal with the deal with like ReLU functions, you need to use the polynomial approximation. And if you use third generation like DINN, you use bitwise encryption, then you can deal with ReLU easily. But the large-scale multiplication and addition is not very friendly for the third generation. So there are also a new type of solution. The new type solutions called switch. We can switch between the wordwise scheme and bitwise scheme, like Chimera, Paxos, and Glyph. However, I think we also solve these solutions in some other way. So let's take a look at how Privasea solved these two problems. Our Privasea face feeder recognition system uses FHE to perform secure biometric authentication. This system can check the similarity between a person's live image and their ID photo. So ensure both similarity check is the person holding the ID, the same person showing in the ID photo, and also the liveness check. So is the person holding the ID physically present during the transaction? So is he or she a real human? That is liveness check. The workflow is as follows. We use ResNet, maybe ResNet 18 and ResNet 34 to extract the encrypted embedding vector, and use FHE to realize face recognition homomorphically. But it's very costly, so it takes minutes or 10 minutes, more than 10 minutes. So to enhance the performance, our system employs two key solutions in our application. First, we divide the model. Let's consider a few questions. So what data is really sensitive, the picture or embedding vector? You know, if you use DINN, then DIN encrypt the whole image, but locally evaluate the extract processing. So we think that for client, which one will out of control? Then it's really the sensitive data. So I think it's vector. We divided the model, and the feature extraction part was completed locally on the client set in our application. So it's in the plaintext state, and then the extra feature vector result will be encrypted and transmitted to the server. Then the server only performs homomorphic comparison operations. That is more easily to evaluate. So the second core solution is that in the original model, the comparison operation was achieved by calculating oscillating distance. But it's a homomorphic unfriendly function because it's a lot of power of 2 and a lot of squares and so on. So we retrain the models using a cosine distance and calculate the cosine distance through inner product operation, like the second formula. And then the result is that we can achieve homomorphic facial recognition in seconds. Maybe if you use our application, maybe 3 seconds or 5 seconds. Okay, So privacy FHE-based face recognition can be applied in various scenarios, such as secure KYC, procedures for decentralized applications, and liveness checks for some biometric authentications, and so on. And this is our I'm Human application. You can find it in your in the Google App Store and Apple App Store. So in conclusion, fully homomorphic encryption presents a significantly advancement in the field of privacy-preserving technologies. By enabling computations on encrypted data, FHE ensures that sensitive information remains secure even during process. So the application of FHE in machine learning and biometric authentication, as demonstrated by the privacy network and face feeder recognition system, shows the potential to revolutionize data privacy and security. And then you can access our website also to download our application. And thank you for your attention. So I hope you found this presentation insightful. And I would now like to open the, do you have any question? You can.
Thank you, Ricky.
Thank you.
Any questions? We have a few minutes. Okay.
So yeah, thank you. I have a question. First of all, I want to ask why you choose face for doing this verification. Because for example, like for biometric, you can also do, for example, like fingerprint or something like that. Some also use iris for that case. Why you use face? What is the, because in my opinion, face is kind of hard because like you have to kind of like take a picture and then try to extract all the features, and there are so many features. For example, for fingerprint, you have, you still have some abstract features that you have to extract, but I think it's more simpler, I would say, in my opinion. And then why you choose to use blockchain for distributing the computation? Because like, for example, you can just use your private own computation instead of blockchain. Why you choose to publicly outsource this kind of computing? That's my question. Thank you.
The first question, if we use, why we choose face is because it's, we have trained this model for maybe 1 month before we decide to do this application. We have trained this face recognition models to, we use we use cosine distance instead of oscillating distance. It's not very simple to deal with another situations, right? So the second problem is that we want to use blockchain to use the distribute computing power, because we can then use a lot of there are a lot of free powers, but if we use a target evaluation powers, it's more like a centralized one. So we use decentralized one to deal with like trust problems. FHE is only it can provide your privacy, but it can't make confidential. It's not like ZK. So we have two solutions. The first one is we want to make ZK FHE, but ZK FHE is very slow. We try to make a zero knowledge proof of simple the search generation bootstrapping, and maybe 10 minutes. So then we use a blockchain to solve the trust problem. Yeah. Thank you.
All right, we have time for one more question.
Hi, thanks for the presentation. Do you have any result regarding memory usage or time?
Maybe you can use our app and maybe 3 minutes, 3 seconds, or 5 seconds. Yeah.
What kind of setup did you use? You're meaning?
You say our server or just your phone?
Oh, okay.
You can use your phone, yeah.
Okay, thanks.
Thank you.
All right, thank you so much, Ruki.
Thank you.